All right, number 6 out of chapter 5. And we're going to do it by method of section. So it starts exactly the same, obviously, as the joint method. We have to find the reactions. So when you see symmetry, just be super careful with this. But if you see symmetry, then you have symmetrical loading conditions all the way through. Both symmetry in the truss and symmetry in the loading will produce symmetry in the reactions. So if you see that, you can just make that assumption. That's legit. If there was an X load on this at all, then symmetry is gone. You got to do your moments to figure out those reactions and go for it. But we have no forces in the X, so AX is equal to 0. And we have a symmetrical truss and symmetrical loading. So you can take the full load, which is 60, and send half each direction. Just don't make that assumption if there's any non-symmetrical loading or any non-symmetrical condition in the truss. You just can't do it. All right, so method of sections. Once you have your reactions, you choose your method, right? I want to do method of joints or I want to do method of sections. So what the book's going to start to do is it's going to start to say, hey, what's going on in member BG? Right, it's going to start to identify certain members that we want load condition for, but we really don't care about the rest of them for some reason, right? So this can happen in really long trusses where we know the primary loading problem is going to be in the middle of the truss or near the middle of the truss, right? So we just want to learn what's going on in the middle of the truss, designed for that, knowing that all of the other members outside of that kind of middle zone are going to be lower loaded. And if we build the truss out of the same members, which is super common, you go across the steel bridge, those steel members, they're all the same member, even though some of those are not loaded at all. And some of them have a third the load as the heavy loaded member. We still build them out of the same thing because it would be too complicated to put, 4-inch W shapes in one area and 12-inch W shapes in another area. How do you connect that up? And it just becomes problematic. So we tend to use the same members. Sometimes we will upsize the bottom chord because it tends to carry more load. So these, like if this was a wood truss, you'll see these as like 2x8s. And then you'll see these diagonals and verticals as 2x4s, right? They've just upsized the heavier loaded members and then saved some resources on the other members. So we do like to target members and learn about them. So let's say that BG is the member we want to find. Right? So that kind of automatically throws you into section. We really don't want to have to go from A to F to B to get BG. We want to kind of go straight to it. So the method of sections says you can section a truss. You can cut it. You can cut it anywhere you want, as long as you're cutting 3 members or less, because we have 3 equations. Some forces in the X, some forces in the Y, some moments. So you can cut through a truss anywhere you want, as long as you're not cutting more than 3 members. You can cut 2. You can't really cut 1. There's no truss that has just 1 member sticking out somewhere, right? So, and then obviously you want to cut through the one that you want to find out about. So this is the logical cut, is right through that vertical area. And you do kind of show it somehow on your truss, so everyone knows where you've cut it. You can have a prettier cut line than mine, or you can have the same cut line, doesn't matter. But then the concept is when you cut it, everything you cut will turn to forces, okay? And the rule is you just assume everything in tension, because this is way too complicated to figure out tension and compression. You can work with either half of the truss, because you just cut it in, maybe not half, but you cut it into two pieces. You can work with the left piece or the right piece, either one. I would say work with the one that has the least amount of things going on, the simpler side. So over here, on this side, there's 1, 2, 3 forces. On this side, there's 1, 2, 3 forces, but there's a little more space and activity over there. But honestly, either side is going to work just fine. Okay, so you choose. I'm going to choose the left side. Now the concept is the parts that you did not cut, we're just going to treat it as a solid structure. So what you end up with is this solid structure and 3 additional vectors, in which we assume all of those in tension going away. So this is BC, this is BG, this is FG. That make sense? Slicing through 3, turn those 3 into vectors. We are going to ignore the right side, totally ignore it, and we're going to work with the left side, which has to be in equilibrium. Okay? You do end up with 3 unknowns most of the time because you're going to cut through 3 typically. I could redraw it. You don't have to. I tend to redraw it. Depends on how complicated things are. One of the problems with redrawing is if you forget something, right? So I could be introducing error here, but I'm going to redraw it just for clarity. That one's 0. This one is 30K. So this is point A. This is B. It has 10K coming down. It has BC. It has BG. It has FG. You know, this is 20 and this is 20 feet. That makes sense? Anything in equilibrium, any part of that thing has to be in equilibrium. So this is just a part of this. This was in equilibrium, so now this has to be in equilibrium. Then you just apply your equations. Some forces in the X has to equal 0. Some forces in the Y has to equal 0. And the sum of moments, any moment, has to be equal to 0. We can dig out some angles. So I need this angle, theta, for BG. BC is horizontal, FG is horizontal. So it's just that angle that I need. And it's 20 and 20, so it is what? 45 degrees? Yeah, so it's super simple truss. Which means if you ever get a chance to design a truss, keep it simple, man. Use 45s if you can. So now, how do you think we solve for this? Remember, our target is BG. Let's just think about this for a second. If one of these might work better than the other.
Questions on why?
Yeah. How come?
We already have 2 now.
Yep, we have 10, and we have 30, and the only other one is, yeah, the Y component of BG. Excellent. So that Y component of BG is equal to, we got 30 up, we got 10 down, 20K down, correct? That puts it in equilibrium. So that tells me that, oh, if that's down, this has got to be this way. This has to go down. BG is in tension for sure. So yeah, if you can see those things, that's golden. You know, that saves a lot of work. I can now pull BG out. And I know that it has its components. And one of those components is 20K, and that the angle is 45. So this is just extracting BG out. on its own and looking at its components, I can go straight to my answer, which is sine 45 equals 20K over BG. BG equals. No, 20K divided by 45 sine. 28. Anyone else get that? And it's in tension. Boom. If all they wanted was BG, then the problem is solved. A lot of times they're going to ask you for 3. Okay. One other thing I want to talk about, and then we'll call it for the day a bit early. I want to talk about zero force members. Okay. There are members in a trust that are 0, and we can identify those. Once we learn this strategy, we can pick them out, and it can help us because it solves members. Okay. So if I have a connection, let's say connection H, joint H. If I'm going to do an analysis of joint H, I draw it, right? So here's H. I have a vector up, a vector over, and a vector over, and I'm not going to even worry about direction right now. I'm just going to point them all out. But this is H E, this is GH, and this is DH. Everyone good? Everyone follow what I'm doing? That is just a free body diagram of that joint H. Agreed? Okay. How many forces in the Y? 1. Forces in the Y have to be equal to 0. DH is equal to 0. So what you're looking for are T's. These two, GH and HE, must be in the same line of action for this to work. If they were off at all, right? If it looked like this, now how many do we have in the Y? Forces in the Y, there's 3 of them. How many in the X? 2. Forces in the X, there's 2. I cannot identify any 0 force members. So don't do it. I mean, you really want to do it because it makes problems simpler, but you can't. But I can here. I know that one's 0. It's clean. What about this one? What about CG? Not 0 because of the 40. If I drew C, it would look like this. This is joint C, right? 2 in each direction. I cannot identify a 0 force. Can't do it. So look for them because they're handy. What about BF? You have to kind of ignore my scriggles. BF. Yeah, free body diagram of F. And for me right now, I want to see the individual free body diagram if you're going to pull a 0. But it looks like that, right? And so that one is 0, that is BF. Super handy. Very handy. 0 force members are incredibly handy. Questions on that? No? You believe it? It's true? You got to believe it. You got to believe in this class. Now check this out. This is like next level, 0 force members. Do you see any zero force members? I see a lot of drawing. Look for a T. Take your time, look at it. I shouldn't draw in my book. All right, where do you think they're at? Yeah, BH looks like it might be 0. And opposite side, FL. Yeah. Very good. All right, I'm going to just sketch this thing, because I don't want to draw in my book anymore. But I'm not going to make a beautiful sketch. I'm just going to get it done fairly quickly. It'll actually be faster if I use a straight edge. So how many points? 2 points up, 2 points. And then we're just vertical. Each one has a vertical. And then we are diagonal and diagonal. I think it's like that, yeah? Yeah. All right, here it is. And you identified this as 0 and this is 0, yeah? They are, for sure. The only way they could not be is if there was a load coming down on either one of those, but they are definitely 0. So A, B, C, D, E, F, G, H, I, J, K, L, M. Oh, no M. Good. So now I'm going to teach you the contagiousness of zero force members. So once you determine for sure that this is 0, it's 0 at both ends. Does that make sense? It's got to be 0 at both ends. So that means the new connection at F looks like and I'm going to exaggerate this. It's like this, right? Where we have FK, FE, FG. Yeah, this is a good party trick, Junior. You can pull this out at a party and teach everyone this. They're going to love that. Yeah, so this agreed, that's the new connection because this one is now gone, the vertical one, it's 0, right? So now check this out. As long as these two are in line, and I'm going to actually rotate my paper a little bit, and I'm going to say X is here and Y is here. Because I can do that. I can put the axis anywhere I want. How many forces in the Y direction? There's just one, and it's this Y component. And if there's only one in a direction, it's got to be equal to 0. And if a component is equal to 0, then the force itself is equal to 0. It's for true. It's crazy, but it's true. The key is these have to be in line. That's why you see trusses that are made like this. You all seen these kind of trusses where they have a kind of a hitch in them? I think they're called barn trusses or stuff, something like that. That's so you don't get zero force members. Well, you eliminate them when you kick those not in line, like this and this are not in line, right? Well, these are in line. So this is 0. Got to be. So I'm going to put a loading condition on. I'm going to put it on here. And I put it on here and here. So now we have a loading condition. Still 0, still 0. If I look at K, because now this one's gone, what do you think? Definitely 0. based on this connection, not based on this connection, you could never determine that. But based on this connection, that's got to be 0. Now, what about if I go here and think about this member, JE, EJ, what do you think? Not, because we have a vertical load coming down. So that vertical load stops this flow. If it wasn't there, that goes to 0, right? And then the other side, 0, 0, boom, stops. Oh, 0 based on this. So they can be contagious. When you find a 0 force member, look at the other end and just see what's going on. But don't force it. But if you didn't have that load and that load, you would go 0 and 0. How? Absolutely. From right here, 0. All of the internal members are loaded, which all this is saying is that's what it looks like, load condition wise. Well, that was the first problem we did. Yeah, we know this is a truss and that works. This load comes down, travels down these cords, delivers it to the supports. It's true. So why do we have all this in here? Yeah, absolutely. In case the wind blows or the earth shakes. Because then shit's gonna hit the fan. But yeah, some of these trusses, these longer ones, are unloaded. If you look at like the Morrison Bridge or the Steel Bridge and like block off both lanes and don't send a car across, you have a bunch of 0 force members. But now take a semi truck and drive it across and you just watch them load, 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 load. You know, they all just get loaded along the way. Or traffic jam all the way across and now the whole damn thing's loaded, right? So the Fremont, that's the big bridge in Portland. That loading condition, the design loading condition is the maximum heavy truck haul, like a semi truck, the maximum heavy truck haul, top deck completely full of those trucks, bottom deck completely full of those trucks. And now the earth shakes. That's the loading condition. It's crazy. But everything's loaded in that loading condition, right? If you ever get in a that's the coolest bridge. If you ever get in a traffic jam, like on the upper deck of the Fremont and the bottom deck is still going, shit, your car almost jumps off the bridge. Like it starts hopping around because that whole bridge is flexing so much because it really wasn't designed for the 2 halves to not move at the same time. It's an incredible amount of deflection. It's like, whoa. What is happening? I thought it was an earthquake when I got stuck on it. Because literally the car is like jumping around because that lower deck was just still booking across. And you could feel the deflection as vehicles went across. It's crazy. All right. 0 force members. Look for them. A lot of the early trusses we do, you're not going to see many. But when you get into sections, you could see them. They could pop up. So just kind of try and identify them. Obviously, you know, something like this happens, helps a lot. Like you just solved all the internal members. You just got to make sure you're right and you're not forcing it. Okay. All right. That's it. Good luck on your homework.